So the next topic is modes of operation. Modes of operation is a technique that enhances the effect of applying a cryptographic algorithm. It is intended for use with block ciphers, and they can be used with any symmetric block cipher like 3DS or AES. So what does modes of operation really do? Let's talk about the first type of modes of operation, or the first mode, that's called electronic codebook mode. It just says that whenever you have a plain text, you encrypt it with a key and you get the ciphertext, and you do that for the remaining plain text in the file or in the information that you're sending. To decrypt, you do the opposite. You get the ciphertext, you decrypt using the key, and you get the plain text. It's very simple, very easy, but it has some weaknesses. The weakness is that for any given key, there's a unique ciphertext for any B block of plain text. And for lengthy messages, ECB may not be secure. Why? Because if the plain text appears multiple times, the same ciphertext will appear multiple times. And this allows cryptanalysts to infer some information about what's being encrypted. If P1 and P2 and P3 are the same, then C1, C2, and C3 are going to look exactly the same. Then an attacker can know that these three are the encryption of the same plain text. So it doesn't hide the information very well. And you will understand that better in Lab 6. So people came out with a mode that's called chain block ciphers, which requires something called an initialization vector. This initialization vector gets XOR'd to the plain text before it gets encrypted. And the output of that encryption is chained into the encryption of the next coming plain text, such that if P1 and P2 are the exact same plain text, the output of P1 is going to be different than the output of P2. So if an attacker looks on the output here, they will not be able to know that the plain text for C1 and C2 is the exact same plain text. So notice here that we're not encrypting the plain text right away. We're encrypting the plain text XOR'd with a random value that we call initialization vector. And we're not encrypting the plain text 2 right away. We are encrypting the XOR'd version of it with the output of the ciphertext from the previous operation. And this is why this is called chaining, because whatever output comes from the first block gets chained to the next operation. In decryption, you take C1 decrypted, and whatever comes out, you XOR it with the initialization vector, and this is your real plain text. The next ciphertext you decrypted, and then XOR it with the previous ciphertext, and this becomes your P2, and that process is what you do until you reach the end of the ciphertext. So what CBC adds is an IV initialization vector that is XOR'd with the first blocks of plain text, and that makes, and every following ciphertext gets chained into the operation of the next plain text. And this makes sure that if the same plain text block was repeated, it produces a different ciphertext block. So this one hides the properties of the plain text. One problem with CBC is that encryption is slow because you cannot encrypt in parallel, because you always have to wait for the first plain text to get encrypted in order to encrypt the next block, and you have to wait for the P2 to get encrypted in order to encrypt P3. So the chaining affects the efficiency. To overcome this, we get to the point where instead of chaining, we have some salt. It's not called salt, it's really a counter. and we encrypt the counter instead of encrypting the plain text. And because it's a counter, then we can do all of this process in parallel, and then whatever comes out from counter 1 is XORed with plain text 1, whatever comes out from counter 2 is XORed with plain text 2, and so on until counter N with plain text N. So this makes encryption more efficient because you can do all of this in parallel. You don't have to wait like the CBC as we talked about it. In decryption, you decrypt the counters or even encrypted, and you XOR it with the ciphertext to produce the plain text. So this part here is very similar to the stream ciphers that we talked about. They were very simple in a way that it only relies on XOR. The hard encryption really happens here on the counters. That way you have more efficient encryption and decryption process. It allows for parallel encryption or multiple blocks, and the ith blocks of the plain text of the ciphertext can be accessed randomly. It doesn't have to happen in order or sequentially. And that's called the counter mode. 3 simple modes of operation. There are more modes of operation. There's one that's called the Galois mode of operation. We'll not get into it, but you will see it later on in the course when we get to discuss SSL and TLS. But so far, these are 3 general modes of operation. Lab 6 should show you the difference between ECB and CBC. It will ask you to encrypt information using a picture. You will encrypt it once using ECB and once using CBC, and you will open it as a picture, and you will see that you can still know what the picture is from the ECB encrypted information, but you cannot know what the picture is from the CBC encrypted file. You will do it on the Kali VM that you have, and the directions are on the live schedule.